Hey everybody. In this lesson, we're going to start off our final unit on two variable statistics, cause and effect, by looking at correlation. So it's not going to be really heavy in terms of abstract concepts. There might be a few calculations we're going to do by hand and some using technology. So it should be pretty low-key. Hope you guys enjoy. Let's get started. So we're going to start off with a little investigation, little motivation problem. I want to say I have this data in table form is I have already entered in a Google Sheet, and I have shared that link with you on Brightspace. So you'll be able to follow along with me. You don't need a handout for this. So here we have, and this is completely fictional data, just made up for this purpose, but it'll do fine. So we have a study that examines two dog training methods, and the dogs were randomly selected, and they received from 5 to 16 hours of training in either the Rogers method or the Lang system. Then they were given a test, and their test score was out of 20. And then here are the results. So what we'd like to do is we'd like to see, which system is better. Like if we had a dog, we want to get trained, we want to make an educated decision, we want to find the best method, right? So to start off, let's use the tools we have at hand. Let's find just the average hours trained and the average scores. Maybe we can see what does better. Because if like say they each train for 10 hours, but the average score for Rogers is like 16 and for Lang it's like 12, then we could probably say that Rogers is better. But right now, just looking at the raw data, we can't really tell anything. So head over to my Google Sheets that I've shared with you guys. So here I have the data here. So let's find the averages. So equals average of these guys, enter. Okay, so the averaged hours training with the Rogers method is 10 hours. And I strongly encourage you guys to do this too. Just having these skills and having like brushed up on them, it's going to make your work this unit a lot easier. We're going to do this stuff a lot. So I'm just copying this formula and I'm pasting it, and I got now I have the average score for the Rogers method. So on average, they trained 10 hours and had a score of 11.5. Lang system trained for 10.2 hours. So pretty much the same. They trained these random 10 dogs each had, roughly the same amount of training. And a score of 11.5. So right now, we can't really tell anything. Like it appears that these systems are the same. On average, these dogs each train for about 10 hours and have a score of 11.5. But let's go further. So we've got these values on their spreadsheet. We've just talked about it appears they give the same results. So I'm not going to fill this in. I'm just going to talk that through. So one variable stats are not quite enough to analyze which training method is better. The sets of two variable data or one variable stats aren't enough. So, but luckily you guys already have a tool, most of you developed in your grade 9 course, to analyze two variable statistics, and it's the scatter plot. So today we're going to look at scatter plots in a bit more detail. So why don't we look at a scatter plot for each of these training methods? We'll look at hours trained as the independent variable on our horizontal axis and look at the score on the vertical axis. And then maybe we can see if there's any new light shed on this. I'm actually just going to highlight all of this data, including the labels as well. This is just going to help you have a fully labeled scatter plot when you make it. You don't have to do anything, which is great. So insert, chart, and the default here is going to be a scatter plot, which is wonderful. So hours on the bottom, score on the top. Perfect. Make that a bit smaller so I can fit everything on here. And now we'll just do a separate one for the Lang system. Data and labels, insert chart, and the default here again is scatter plot. That's great. So, you guys did a lot of scatter plots in grade 9. You made a lot of scatter plots by hand. I'm not saying we'll ever do a scatter plot by hand, but we're mainly going to use technology, right? We want to be doing higher level stuff and not have to spend all our time just making simple scatter plots when technology will do that for us. Okay, so now we can see, hey, there might be something more to this story. If I were to describe the Rogers method, it appears that as hours trained increases, the average score increases too, which is kind of what you don't want in a dog training course, right? You want to know if you're going to pay for these training hours, your dog's going to get more obedient, right? For the Lang system, I would say we can't make that case. The scatter plot, the data points kind of appear to be randomly scattered. We'll find out later, but maybe even going down over time. And I can't really say any pattern, like, whether my dog trains for no hours or a lot of hours, I can't reliably predict how their obedience is going to be, but I can with the Rogers score, right? So a scatter plot is a 2-variable statistics tool that can often tell you a lot. So after doing the scatter plots, I think that we would conclude that the Rogers method is better. And the characteristics we see is that we can see this trend, right? As hours trained increases, score increases. The Lang system, no real trend is obvious, right? So questions like, does smoking cause lung cancer? Which I think everyone, that one's been studied a lot, and there's probably an obvious answer. But sometimes the answers aren't so obvious. Like, is job performance related to marks in high school? Do pollution levels affect the ozone layer in the atmosphere? And again, like, some of these questions are obvious, but some of these aren't. Does a driver's age affect the number of fatal driving accidents per year? So when answers aren't clear cut and you have to make inferences, 2-variable stats provides methods for detecting relationships between variables and developing like models, equations we can use to make predictions and analyze. So we are going to focus on 2-variable statistics. The reality is things like the number of fatal driving accidents per year can depend on tens, hundreds, thousands of variables: age, gender, socioeconomic status, what car you drive, so many things. In reality, things depend on many variables, and there are tools to analyze multivariable statistics. That's more for a post-secondary course. I did things like that in a third-year stats course when I studied at Waterloo. So today in this unit, we're just going to focus on stats of 2 variables. To visualize a trend, if we look at data collected over a long period of time, it might show trends and allow us to make predictions. That's ultimately the goal for us, is to see a trend, be able to get a model for that trend, a mathematical model, so we can make predictions. And again, an effective way to do this is a scatter plot. So here's a scatter plot showing the Canadian population from the years about 1970 to 2006. Now, depending on like how much math you've taken, like some of you guys might, who have taken we've all taken a grade 11 math course. You guys have all learned about exponential functions, but you might think, well, population growth is exponential. Looks like this. In this case, zoomed up for a very small part of, Canada's population growth. The trend illustrated here, it definitely appears to be linear. We are going to analyze, look at nonlinear trends as well. But to start off, we'll talk about linear. And a graph like this might be useful. So say instead this wasn't a Canadian population, but it was a population of like a small town. Maybe like I live in Guelph, so Guelph has around 100,000 people. But if you're a city planner, you would definitely be interested in, what's my population going to be in 2050, right? Because city planners and like any kind of civil engineer, they need to plan roads and infrastructure. So you might really be interested in what the population is going to be in 30 years. And not only that, you might want to know, like, have other information on not just population, but demographics, what age groups are, what kind of jobs are coming to town. You might be able to want to predict those in the future so that you can, plan for your city. So that's all kinds of reasons why a graph like this might be useful. But to make predictions is probably the biggest one. So scatterplot helps us reveal those relationships that shows a general trend in the data, like the dog training example. The arrangement of the points helps determine the type and the strength of the relationship. So I would just be curious what you guys think about these 4. So would you consider these to be strong, moderate, or weak correlations? So in a bit, we're actually going to give a more guidelined way to identify whether it's strong, moderate, or weak. But just take a moment and maybe you want to jot down your thoughts. Hopefully, and you can unpause when you're ready if you've paused it, or you might just want to follow along. But I'd say this is strong. It almost looks to be in a perfect straight line. So in those cases, we might almost say perfect. And because as X increases, Y increases too, we would actually say this is a strong positive correlation. The second guy is positive as well. As X increases, Y increases. Now, whether you said moderate or weak or strong, like really who can say, right? It's a matter of opinion. And again, we'll develop tools for classifying these in a second. I personally might say moderate, like I don't know. But there's really no wrong answer right now. Moderate, positive. In the third example, as X increases, you can see that the Y values are decreasing, right? So we would call this negative correlation. And this one's pretty strong. And it almost looks like they're in a perfect straight line. If it's a perfect straight line, you would say it's perfect correlation. In this case, it's negative. And this last one, maybe you said weak, maybe you said moderate. I mean, right now, as I said, there's really no wrong answer here. We might say that's moderate negative. But I think we can all agree on the positive and the negative. As the independent variable increases, if the dependent variable Y increases, it's positive correlation. And if it decreases, it's negative. So this is kind of the extent you go to in grade 9 and just classifying by looking at a graph. So again, we're going to develop a math tool to identify strength of correlation. The way we do that is by calculating what we call this correlation coefficient. Correlation coefficient is sometimes a mouthful. It's denoted by the variable R. So often we'll just say R value. But what we're actually talking about is the correlation coefficient. So it's a numerical statistic, and it's a 2-variable statistic. So this is our first 2-variable statistic, whereas in our previous unit, everything was like, here's a set of values, and we had all these 1-variable stats, mean, median, standard deviation. This is our first statistic that relies on 2 sets of data, the independent variable X and the dependent variable Y. And you can see it's pretty detailed. Everything on the bottom here actually is under the same square root, and it involves a number of data points, n. It involves a bunch of sums, totals, the sum of the X values, the sum of the Y values, the sum of their squareds, and even the sum of their product together. So this is definitely not very practical to do by hand all the time. That said, I actually like to do at least a few by hand in my initial lesson just to get a feel of how it's calculated. And then in the future, after today, we will only use technology to calculate this because this is just too cumbersome to do all the time. That said, though, we're going to have a bit of fun. We're going to test out this formula. And then I'm going to show you guys how you can calculate this in a spreadsheet program. So here we have a set of 10 data values. So here, n is equal to 10. And if you look at the formula here, there's 5 sums you have to do. You have to you have to find the sum of the X values. That appears a couple times. You have to find the sum of the Y values. That appears a couple times. You have to find the sum of the x and y values multiplied together. You have to find the sum of the squares of the x values, and you have to find the sum of the squares of the y values. So first step would be, can you guys complete this table? And I promise after today and your little task that I have for you later, we won't be doing any more by hand, but it's just nice to get a feel of how it's done. So I would recommend pausing the video. If, at the very least, you can get the table done and then pause the video, and we'll see how the formula works. If you'd like, in today's lesson, on the spreadsheet I've shared with you guys, I do have a tab at the bottom. So for our best in show dog training example, I have a tab, but I have a tab for this just example we're doing. So I have this here. So if you'd like to create some formulas to do the totals, like that's up to you, or crank them out by hand. I assume that you've paused and unpaused to give this a try, or you just want to get to the answer. Here we go. So here are my totals. I did double check these with the spreadsheet program. Having got these totals, so here's how you use the formula. So n is 10, and the sum of the x times y, that sum was 1,246. Minus, multiply the sum of the x values and the sum of the y values, 100 times 115. On the bottom, you have a big square root, and there's two chunks you have to calculate. You have to calculate the number of data points times the sum of the squares of the x values, which I got to be 1108. And then you subtract the sum of the x values squared. So that was 100 and squared. And you do the same thing with the y values. The sum of the squareds, 1415, 10 data values, subtract the sum of the y values, all squared. I did this into chunks. I did the entire top at once. I did the square bracket at once, and then the second square bracket at once. And then I found each of those calculations to be manageable. And I got about 0.96. So what we need to talk about is, like, what is the significance of that 0.96? What kind of values can R be between? I want to show you guys, well, I'll show you guys how to do that, but I will actually want to introduce now how you can find this R value in the spreadsheet program. So I'm going to go back to my spreadsheet here. So here's my table. I am going to make a scatter plot of this like I did earlier. So I'm just going to grab the X and Y values, insert a chart. I don't really care too much about the labels for this one. So to calculate this correlation coefficient, in at least Google Sheets, there are lots of other spreadsheet programs out there, Microsoft Excel. I might use Desmos once in a while too. But to do the R value, it's pretty simple. So you have to click on a data value. Notice how you hover above one, they all get selected. So click on that. And we want to scroll down. This gives us a chart editor. And we want to add a trend line. So you click on the trend line option. And you'll see a line of best fit. In our next lesson, we'll talk more about lines of best fit and linear regression. But there's an option down a bit further called Show R Squared. And when you click Show R Squared, it says R squared equals 0.923. We'll talk more about what R squared. This is called the coefficient of determination. We'll talk more about that later. But that capital R and our lowercase r are actually related. The correlation coefficient is the square root of this guy here, 0.923. So if I go back to, where are we here? There we go. So what Google Sheets told us, I don't want blue, I would like yellow. Google Sheets told us that our R value squared is about 0.923. So if you square root that, now here's the thing, correlations can be positive or negative depending on if your data goes up or down. But when you square a number, you always get a positive. So when you're finding the R value from the R squared value, you just have to be careful that you look at your data and say, well, is it increasing or decreasing? Our scatter plot said it was increasing. So R is going to be positive, the root of 0.923. And if you guys do that, you'll see you actually do get 0.96. Our formula checked out, but moving forward, we want to rely less on the formula and just do things using Google Sheets. But that's the secret is find R squared and square root it. In this case, it was positive, so positive 0.96. But if our trend line went down, then we would use negative 0.96. All right, so clearly our value is messy to compute by hand. We'll use technology. I just showed you guys how to use technology, at the very least, how to use Google Sheets, and maybe another day or lesson, we'll try a different tool. So you know how to do a technology, and here's how we can interpret the strength. What does the value of R mean? So R can be between -1 and 1. And if R does equal 1 or -1, and that can happen sometimes, we call that perfect correlation. That means that the X and Y values form a perfect straight line. They're perfectly correlated. You can perfectly predict the later Y values if I give you the X value. So it's kind of like a number line. R can fall between -1 and 1 with 0 in the middle. And then this isn't by any means the only way to classify them, but I think this gives us a bit of detail. So you can, if you think about breaking this up into chunks, you can now say, we can now have some language we can all use to say how strong the correlation is. So if the R value, at least its size, is between 0.8 and 1, we can say that there's a very high or very strong positive or negative correlation. And I personally don't care which you use, because it's all kind of subjective anyway. Between 0.6 and 0.8, you can say a high moderate. Between 0.4 and 0.6, moderate. 0.2 and 0.4, low. 0 to 2, very low. Or even at this point, if you said none, like, that's legit too. Again, this isn't a formal way. Different teachers have their own. Some people just like to use strong, moderate, low, and I have in the past. I like this bit of detail, actually. Just gives you just, more language to compare different sets. So later on, we'll look at when we throw in a third variable. But I want to stress this R value. It might tell you that two variables are correlated, but it doesn't tell you about cause and effect. It doesn't tell you that one causes the other or the other causes that one. It just tells you they're correlated. We don't know why. So we'll talk about cause and effect later. But right now, this R value only tells you that they're related somehow. And again, to get the R value, you take the root of R squared, which many spreadsheet programs will give you. But just remember to take the positive or negative depending on if your graph goes up or down. All right, so let's wrap things up by actually going back to our dog training program. Let's find the R squared value for those guys, and then hence the correlation coefficient. So let's do Rogers method first. All right, so I'll click on a data value. Okay, got to bring up my chart. I think there's a way to get a chart editor. Is it chart style? Chart editor, yep. And if I click on a data value, there we go. So let me add a trend line, scroll down further, show R squared. Okay, so for the Rogers method, it was 0.923. In my table here, 0.923. Was it just the Rogers method the whole time? 10, 11, 15, 15. It was the Rogers method the whole time. I knew there was a reason I did that. We already got the Rogers method. That's fantastic. So where are we here? Where's my PowerPoint? There I am. Great. And then the R value we already did was 0.96, and we knew it was positive. So, very strong positive correlation. for the Rogers method, which is what we want, right? We want to know that if we train our dog with this program, the more hours we put in, the better the score is going to be. Let's look at the Lang system. So Lang system, click on the data values, add a trend line. And actually you can see that the trend line for the Lang system is actually going down. And we'll show the R squared value. So the R squared value is 0.032. To get the R value, take the root of that. So the root of 0.032. And we know from the graph that it's a negative trend, right? So negative 0.18. So weak or even no correlation. And it's negatively correlated. So now we can actually for sure say, hey, the Rogers method is a better method, right? We know that there's a strong correlation between hours trained and score, which is what we want in a dog training method. So what you guys should be able to do after today is obviously make a scatter plot and make one using technology. Fully labeled, I suggest using Google Sheets. I might use other programs as well later on. Know how to use that program to calculate R squared and hence the R value correlation coefficient. Be able to calculate a correlation coefficient by hand using the formula. I'm going to have you guys do a couple in the task for today, and that'll be it. And classify correlation. And we'll use this table for our class as a bit of a guide. It's not the be all and end all, but it'll work to help establish just a clear frame for all of us to use, a language for all of us to use. All right, so I don't have any like textbook practice or anything today. Today I just have a task for you. It's pretty straightforward. You're making some scatter plots. You're calculating some R values. You're using technology to check. It should be pretty chill. So I hope you guys enjoy. Stay well, and we'll see you guys soon.